I'd like to show an example of how to solve a problem using conservation of momentum. The problem we're going to look at, in particular, is a problem where we're trying to figure out the initial speed of a bullet that's been shot out of a gun. And we're going to do that by firing the bullet so it embeds itself in a block of wood. A block of wood is bigger, easier to measure its speed. We measured that after the bullet embeds itself in the block of wood and it starts skidding away, that speed of the block is 4 meters per second. We know the bullet is just a 10-gram bullet. The block of wood was chosen to be a 1-kilogram block of wood. And so our goal is to figure out what the initial speed of the bullet was based on this data. This is a perfect problem for using conservation of momentum because momentum is a perfect way of analyzing systems where you have a before and an after, and you don't really care about the details of exactly what happened in between. There's some complicated bullet squishing into wood process there, losing energy, combining together, starting to move. I don't care about those details. I want to compare what happened immediately before that collision to immediately after. So the first step I always take in one of these things is to draw a picture, just to clarify in my mind what's going on. So let's see. To draw a picture, I have this is my before picture. And in my before picture, I'm going to have a bullet like this, moving with some speed. I guess I don't need an absolute value here. Some V initial for my bullet, and it's moving toward a block of wood, which has a mass m wood. The bullet has a mass m bullet, and the block of wood has V wood initial equals 0. It's sitting still to begin with. That's my before picture. I'll also draw an after picture. For my after picture, it's going to look a little bit simpler. I'm just going to have this block. I suppose there's a little hole in it here where the bullet has embedded itself inside, but the whole thing now is moving with what I'll call V final, the final velocity of this combined system. They're moving together at that point. The bullet has come to rest inside the block as the whole thing moves together. And so that's my final situation. Okay, I've got a before and after. And the thing to look at here, I have to make some assumptions to be able to make this conservation of momentum problem that will work well. In particular, I'll note that this is a collision. And as a collision, the idea of it being a collision is that the bullet's impact is the biggest effect while it's happening. There may be friction and things that come into play later, but while the bullet's hitting that, nothing is more important. So is the biggest interaction by far during the collision. So that's why we can look before and after. This is, things may change quickly afterward, but we want to look at before and after to see what happens. The bullet's impact is going on, so we can use this as an isolated system. So it's approximately isolated, which means that there's no significant external, that's supposed to be external, no significant external transfer momentum, external impulse involved in this problem. So okay, we've got that. Another thing I want to do, since I have these pictures up here, is choose a reference frame, choose a coordinate system. I'm going to go ahead and choose my plus x direction in both pictures to be to the right. I don't care about y really, it'll be upward or something, but all the motion is along the x direction. I'm choosing my x direction aligned with that. So I've got that drawn into my pictures. That's good. And at this point, it's useful to make a list of our known and unknown quantities. Things that I know, for example, let's see, I know that the mass of the bullet is 0.010 kilograms. I'm converting from grams there just to have a consistent story. I know that the mass of the wood is 1.0 kilograms. Got that story from over here. I know that the final velocity vector is, and I'm going to use our column vector form to write this down, our final velocity vector is 4.0 meters per second in the x component and 0 and 0 for the y and z components of that vector. Those are my known quantities along the way. And I guess I should say v wood initial is 0, and then my big unknown is v initial of the bullet. That's the unknown that I'm really aiming for in all this. I want to know the initial velocity of the bullet, and that's where I want to come from. So I've set up the problem. I've got a lot of basic information collected. This is a perfect example for conservation of momentum applying because it's an isolated system. Oh, this was supposed to say is approximately 0. That's why we can use conservation of momentum. We've got that, and so I'm going to write down my conservation of momentum equation, which is just to say that the total momentum initially is equal to P total finally. And to write that out more explicitly, I'll have P bullet initial plus P wood initial equals P both final, both of them together, moving at the end. And what do we know? We know the definition of momentum, right? We know that P bullet initial is equal to the mass of the bullet times V bullet initial, and P wood initial is mass of the wood times V wood initial, and P momentum of both vectors final is equal to the total mass of the wood plus mass of the bullet, times V both, I guess I just called it V final, didn't I? Times just V final vector. So those are my definitions of momentum for these different cases. All right, I have these pieces. So where can I put this? What can I do with this? Well, I suppose what I really want to do is just put it together into an equation. I'll see if I can fit this over on the side here. We'll do our best. So one thing I can do right away is notice that V wood initial was 0. So this one is just 0. There's no momentum contributed from the wood initially because it isn't moving initially. So that's going to tell me then that P bullet initial equals P both final. Or in other words, copying down, the mass of the bullet times V bullet, times V initial. I guess I just called it V initial here, didn't I? Being inconsistent in my notation? Oh no. This was just V initial in my earlier definition. I'll stick with that. Times V initial vector is equal to mass of the wood plus mass of the bullet times V final vector. The good news about this is that this is vector equation. This is a standard vector equation, and we know how we can deal with these. We're just going to solve for V initial by dividing both sides by the mass of the bullet. And so V initial vector is mass of the wood plus mass of the bullet divided by mass of the bullet times V final. That seems to be a reasonable equation. That's telling me what I want to do here. I just want to have this. I could have divided the whole thing by MB, but I like this fraction because it's got the masses all together. And so, hey, this is a place where I can actually plug in my numbers and see that this is equal to mass of the wood is 1.0 kilograms plus 0.010 kilograms over 0.010 kilograms times my column vector 4.0 meters per second 0. And hey, this numerator, I guess I can write it as 1.01 kilograms over 0.010 kilograms times 4.0 meters per second 0. And the kilograms will cancel out. The units cancel. That's what I hope for in this situation because I want to come out with meters per second as my units in the end. Those cancel. And dividing by 0.01, I can multiply top and bottom by 100 and simplify this out. This is just 101 times 4.0 meters per second 0. That's a 4.0 really. Or in other words, my column vector is 404 meters per second, 0, 0. And that is my final answer. That's my final velocity. In this case, it's all in a straight line. It's in just one component, just the x component. And so I can conclude that this is about 400 meters per second as the bullet's initial speed. If I come over here, I can just report that and say that the speed, v initial, is about 400 meters per second. I could say 404 there, except honestly, I really only had two significant figures in this whole process, so I don't really trust that 4 anyway. So 400 meters per second is my answer, and I got that by solving this conservation of momentum problem. I used component form in column vector form, and it came out to what I hope is a pretty satisfying answer.